Okay, so now that we actually have video, so basically the only sort of administrative stuff is that obviously the project is now out. So hopefully you guys have taken a look at that already. So the first phase will indeed be due basically a week from yesterday, which unfortunately is inside of spring break, but the good news is it should not actually be too difficult in terms of the deliverables for this phase. And in fact, really I wanted to get things out at this point, if nothing else, just to make sure that people really get going and sort of start thinking about what it is that they really want to do. So kind of the key deliverables are actually mostly just kind of a proposal for what are the kind of specs or what are the, let's say, areas that you're going to be targeting to go after. And then also just to make sure that you go and you actually take a look at the channels that I've given you so you have an idea of, you don't just go and say something like, oh, I'm going to do a 100 gigabit per second link and then figure out after the fact that, oh, oops, the channel has 200 dB of loss at that point, and so that's not really going to make too much sense. So how many of you guys have actually already taken a look at the Project Phase 1 handout? Okay, good. Obviously, by the way, this is all in the groups that you hopefully let me know about already. Any questions on the handout in terms of just anything that's not clear or people aren't sure how to proceed? Or wow, I actually got it reasonably clear on the first try. That's amazing. Okay, you'll have more questions on Thursday. All right, sounds good. So unless there's any questions on that, last time we finally sort of finished up talking about equalizer adaptation, and the kind of last area that we touched upon was sort of the practical difficulties you run into when you try and do adaptation for the loop unrolled DFE. I don't think anyone has solved that problem since then, but if you have, then let me know, because like I said, that would be pretty interesting. But fortunately, I think that is a fairly fundamental issue. So any questions on that before we sort of dive into the new stuff? Or okay, so basically what I wanted to start talking about now, which is really going to be sort of not exactly the entire second half of the class, but certainly for the next 2-3 weeks or so, is essentially really diving into some more of the detail of the timing components that you're going to be dealing with. So to really sort of start that discussion out, it makes sense to start talking about essentially phase lock loops and delay lock loops. Okay, so basically, to do that, what I'll just start out with, and I know many of you have seen these before, but I'll just sort of draw a couple of sketches of just sort of what is conceptually a phase lock loop and what is conceptually a delay lock loop. And then we'll see if you guys can actually pick off why in the heck, we might even be talking about either one of these things. Okay, so let's just first sort of sketch quickly what would a delay lock loop end up looking like. Okay? So in a delay lock loop, pretty simple idea. You'll have some reference clock, which in this case I'm going to write it as sort of a reference phase. And you'll see sort of throughout all of the stuff we talk about with delay lock loops and phase lock loops, you're going to have to sort of start getting used to thinking about signals that are actually representing delays or frequencies or things like that as being kind of the equivalent of a voltage waveform. Right? So you kind of would say something like, the phase has a value of x at time y, which sometimes confuses people because phase is a time domain quantity in the first place. But hopefully you'll get sort of used to that fairly quickly. So we basically have some reference phase. We're going to compare that with what's known as a phase detector against some feedback phase, which I'll draw where that came from in 1 second. We'll pass that through some sort of loop filter, and again, we'll talk in a lot more detail about what's exactly actually inside of that thing. And then in a delay lock loop, we'll use that to control the delay of some sort of delay line, which usually, a voltage-controlled delay line, VCDL for short. And by the way, that thing will also have actually some input clock into it. Right? Because if it's a delay line, then you need a clock actually going through the line to actually get any kind of signal, right? So then coming out of that thing is what you'll use to actually compare. And of course, this will be the output of your delay lock loop. Okay? Now again, just to sort of make sure things are clear, I'm assuming many of you have seen similar things before. If what I just drew is a delay lock loop, then a phase lock loop, or PLL for short, of course, is going to be very similar. But now this time, of course, I'm still going to have my phase detector. I'm still going to have some sort of loop filter. But now this time I'm actually going to feed this into a voltage-controlled oscillator instead of into a voltage-controlled delay line. And then I'll have some output over here, and then and I'll draw up a little bit more carefully, take some feedback from there. In many cases, you'll actually divide that frequency at the output, and then feed it back to compare it against the reference input. Okay? So let's actually just start out with the delay lock loop, or the DLL. So why in the heck would you care about something like this First of all, in general, but second of all, specifically in the context of a high-speed serial link. Why in the heck might you need something like that?
Control when the data is sampled.
Okay, you said to control when the data is sampled. So how exactly would I sort of, or what's sort of allowing me, what let's say property of the DLL is allowing me to do that? Yeah, okay, so basically you're adjusting the delay based on some reference signal, right? So more generally, I'd say that this is sort of allowing you to do some sort of clock phase control. Right, now, exactly the way we've drawn it here, the reason I poked you a little bit more in terms of sampling the data at the right time, I didn't give you any kind of data or clock recovery kind of thing here. I just gave you a reference clock and an input clock, but indeed you could muck around with the DLL to try and do exactly what you're saying. Okay, but more generally speaking, you might want a delay lock loop just to sort of control the phase of some arbitrary input clock. Okay? Okay, so we said that that might be good for timing recovery. Any other reasons that you guys can sort of figure out that you might care about this? Where else might it be nice to be able to adjust the delay of a clock? Maybe not even just in a high-speed link, just generally.
Sampler.
Say that again?
Sampler.
Sampler. What about a sampler?
Time interleaved samplers.
Okay. Yeah, that is one application. I'm not sure, let's say that's the most basic one. But yeah, you could potentially sort of use this to get multiple clock phases. So actually, I guess I'll write that. You could do something like this is just to generate multiple phases. And that would sort of rely on some internals of the DLL. But that's true. You could do that. Anything else that's kind of really basic? Something we spent maybe not a lot of time on, but some reasonable amount of time on in 141.
Skew control.
There we go, skew, right? So if you have two arbitrary clocks and you don't really know their relationships, you want to make sure they're actually lined up, then DLL is actually sort of a nice way of doing that, right? So indeed, actually, you'll find these things a lot of times just for the purpose of skew control. And you could actually argue that some of the timing recovery stuff is actually just another way of doing skew control, okay? Okay, so that's indeed, generally a few reasons. Now, by the way, there's a whole bunch more other reasons you can come up with. You might want this just for like edge rate control. As Ida mentioned, you might want this to actually generate multiple different phases of the clock. And probably even about 10 other things that somebody could come up with. But, indeed, that's kind of, let's say, the core reasons you might have a DLL in there. Okay, so now, why might you want actually a PLL? What does that buy you?
Frequency synthesis.
Okay, so you said frequency synthesis. What exactly do you mean by that?
So in the two systems, the transmitter and receiver, they only have the crystal oscillator, but we're operating at a much higher frequency, so you need to multiply that up.
Okay, right. So basically, this lets you do things like basically clock multiplication. Right. So in other words, you can take some relatively low frequency and generate some other frequency at the output that is, at least on average, an exact multiple, right? In fact, you can even do sort of clock division, although that's not particularly interesting, and sometimes even fractional kinds of things. But basically, that's one indeed good reason to have a PLL. Anything else? I'll give you a hint. There's sort of the trivial answer. What's really the only difference between the PLL and the DLL?
DLL only delays the input clock, not generating. So
Right. So basically, the PLL actually generates a clock. Right. So to maybe put that more explicitly, pretty much anything you can do with a DLL, you can also do with a PLL. Right. So pretty much any one of the reasons you may have wanted a DLL, in many cases you could basically apply a PLL as well, and it would also just generate the clock for you. Right? And it doesn't necessarily tie you to have, let's say, the same frequency as what's going in as your reference in the first place. Now, it turns out there's, let's say, some more adventurous things that you could do that would allow a DLL to generate or quote-unquote generate a clock as well. Those are what's known as multiplying DLLs. But once you start playing those games, I kind of claim they look a lot like a PLL anyways, and in fact, you can make a PLL sort of, grab the phase directly from the input also. So, the distinctions are maybe not super precise, but generally speaking, if people say DLL versus PLL, this is indeed kind of what they're referring to. Okay? So again, in our particular context, these are largely going to be important for kind of all of the reasons that we've said here. But in particular, you're generally going to need a PLL and a high-speed link because, for better or for worse, nobody's really invented 20 gigahertz or 10 gigahertz crystals yet. Certainly not, in things that are kind of mass-producible and cheap for you to use. So you are generally going to have to use a PLL for clock multiplication. And in fact, as you're going to see a little bit later on, we're going to oftentimes also use these just because of the fact that they will control edge rates for us or give us an idea about what are some control voltages we can use to actually sort of get controlled edge rates out. Okay? So, indeed, this is going to be something that's going to pop up in a lot of the links that you may end up working on. And so that's why I wanted to spend a couple of weeks really talking about what are the sort of detailed issues in terms of really building these things up. Okay, so to start things out, it's always sort of just useful to think about things in kind of these simplified linear models. And again, this is just to kind of get people used to thinking about signals that are actually delays, also as being sort of a real signal that you looked at as if it has a certain amplitude or a certain value. Okay? So let's just sort of map that block diagram that I drew into something, let's say, in the simplified linear time domain, or I should say really frequency S domain model. Okay? So let's again sort of say that I start out with some reference phase. Okay? So of course, if I'm starting out with a reference phase, the units of that are going to be radians. Okay? Okay, so now as with, let's say, any feedback loop, I'm going to take that reference phase, and basically I'm going to subtract or compare it against some feedback phase, which again, I'll draw where that came from in a second. So this little sort of just subtraction block here, that's kind of like the phase detector, right? It's just comparing the two phases, and in this particular case, or really in general, it's going to convert that error in phase into some voltage signal. Okay? It may actually not be voltage, could be current, could be something else, but generally speaking, it'll be either some electrical signal that you can work with. Okay? Okay, so then once we do that, of course, we're just going to pass that through some loop filter, which I'm just going to call HLF of S. Okay? Then after that loop filter, basically what we're going to be doing is passing that through the delay line, right? And really, what we care about in the delay line is sort of, and by the way, this would also be a voltage over here. In the delay line, all you'd really care about is sort of what's the relationship between the input control voltage and the output delay that you introduce, right? So I'm just going to sort of model that as just being, in this case, some linear gain, which I'm going to call K VCDL. Okay? Now, there's one, let's say, subtlety that you may not have seen before, may not have thought about too carefully. So is this my final output, or is there actually something else coming into my system? And maybe I'll just give you a reminder by showing this picture over here. So is my final output phase totally set by sort of the picture I just drew, or is there one more thing that you have to include?
Input phase.
Yeah, there's an input phase, right? There's actually an input clock that you're feeding into that delay line in the first place. Okay, so in this linear model, there's actually another addition here. And then you take that input phase right here. Okay? Then finally, that's where you get your output. And obviously, or at least typically, that's also where you take your feedback from. Okay, so just to be sort of clear, that KVCDL converts from voltage to phase, so that you can then add in the input phase and get the final output, which is, of course, also in the phase domain. Okay? So now, and this should hopefully be sort of, fairly trivial. So if I wanted to write the output phase in the Laplace domain, what is that going to be? What's that? Well, it's not exactly a transfer function. It's actually going to turn out to be sort of two transfer functions, but what is that going to be?
Be that forward function over 1 plus that forward function
times
the phi ref plus phi in over 1 plus the...
Right, okay. So what Chintan basically said was, for the reference frequency, basically this is kind of your standard feedback block diagram kind of thing. So for the reference frequency, it's just the forward transfer function, which is just HLF of S times K VCDL, divided by 1 plus that forward transfer function. Okay, of course, then times phi ref. But since we have that other input, all the way over there at the end, which basically you can kind of conceptually think of it as if you sort of, oops, let me change the color here. If you sort of flipped the way I drew this loop, you could kind of see that this was purely in the feedback path from the standpoint of that input. So that says that the output phase is then also set by 1 over 1 plus HLF of S times K VCDL times phi in. Okay? So now, if you guys were to just, let's say, take a guess, what's a reasonable, or what's, let's say, the typical thing you might do in that loop filter, and why? What kind of transfer function do you want to put in the loop filter?
Integrator.
Yeah, you want to put an integration. Why do you want an integration?
Because you're only interested in the DC value of the, for you to generate, well, first you want infinite gain at DC to make sure that.
Okay, so right. So the real reason you put an integration there is because you want infinite gain at DC. Because basically you want to make the steady state phase error go to 0, right? Okay, so now, if indeed I use just a simple integration in that loop filter there, then let's just sort of sketch what, let's say, these two transfer functions really look like versus frequency. Okay, so what will that transfer function look like from the standpoint of phi ref? In other words, phi out over phi ref. What would that sort of, roughly speaking, look like?
Low pass.
Yeah, it's just a low pass, right? So it just has some bandwidth, and then becomes, in this particular case, a low pass, right? So that's pretty straightforward. And by the way, nicely enough, this whole system is just a first-order feedback system, right? So it's very, very easy. You don't have to worry so much about stability and things like that. But now, just to sort of make sure it's clear, what is the transfer function from the standpoint of phi in? Yeah, it's a high pass, right? And of course, the corner of that high pass should be exactly in the same place as the corner of the low pass for the forward path, right? So this is basically phi in, and the one in black, of course, is for phi ref. Okay? So I wanted to just kind of go through this quickly because many people, well, I shouldn't say not many people, but for better or for worse, oftentimes actually phi in ends up being the same as phi ref, which usually means that you're using that delay line to lock to like a 1 clock cycle. But then notice that if you do something like that, you're basically not really doing anything from the standpoint of filtering that jitter out. Right? So in other words, that jitter is pretty much just making it straight through your entire system. Okay? Now, that's not necessarily bad. I mean, in some sense, this input jitter was just going to make it through at high frequencies anyways. And you could sort of argue that if your reference was cleaner, since you're not multiplying anything, you might as well just really get the clean reference out. But just kind of keep this in mind, especially maybe in about a lecture or two when we talk more about noise performance and things like that. DLLs do have this characteristic of, especially if you tie the input and the reference together, basically that just phase noise makes it straight to the output. Okay, so there's basically no real filtering that you're doing. Okay? Does this make sense to people, or? Okay. So there's just sort of, let's say, one, or maybe not one, but actually multiple, but in particular, one quote-unquote minor detail that I completely glossed over when I drew that previous picture. So, and maybe I guess I could ask you guys, but maybe just to kind of give you a hint, usually these reference clocks, particularly if I'm in a high-speed link or something like that, my reference clock maybe would look something like that, and maybe my feedback clock would look something, let's say, I don't know, like this. Okay, so now, when I drew that previous model there, and I drew all these things like in the S domain as being continuous and all this other sort of nice, simple kinds of, intuitive pictures. But if these are really sort of your clock signals, what does that sort of imply about how you're actually operating this whole system? Is it really continuous time, or? No, right? Okay, to be totally fair, there are some things you could do that would make it sort of look like it's continuous time, but by the way, at the end of the day, even those sort of really at the end of the day are kind of sampled. So what I'm kind of getting at here is that what you're really largely working with in all of these sort of timing-based systems is actually discrete time types of systems, okay? So in particular, if you really look at how, for example, phase is measured, then if I actually looked at, for example, the, let's say, error phase, which you could kind of think as being the output of the phase detector, in reality, you'd really just sort of treat that as being some sample with a particular value at that sample. Okay? So basically, each one of these clock edges, and let me draw that a little more carefully, you'd basically say that there's some sample of that phase error. Okay? So what this is really kind of getting at is that when I drew that model of the phase detector, so let's say this was my phi ref and this was my feedback, then in reality what I should actually be doing is sampling that output at essentially the clock frequency you're operating at in the first place. Okay? So in other words, now you have to sort of convert that whole system really into the discrete time. Okay, now there's actually one sort of immediate implication from this which can get, people sort of usually will quote this rule but not necessarily understand why it's there in the first place. So what's one sort of like very important implication about the fact that you're actually working with a sampled system and not a continuous time system? I'll give you guys a hint. In this picture here, is there anything stopping me from making the bandwidth of this loop, let's say, 10 gigahertz, just to make up a number? No, right? I can sort of, if I tweaked KVCDL or played with a loop filter, I can kind of make the bandwidth anything I want. Does it make much sense to have a loop bandwidth of 10 gigahertz if your clock is 1 gigahertz to begin with? Who thinks that makes perfect sense? Who thinks that makes no sense at all? Okay, good. No sense at all. Now, why does it make no sense at all? In fact, if you tried to do it, what would happen? Could you get it to work? Okay, no, why not? What's the sort of, let's say, fundamental feedback issue?
Not providing information at Nyquist, basically.
Okay, so you're saying it is you're not providing it information at Nyquist. That's actually, that's correct, although there's, let's say, there's another way of getting some insight about it. Okay? Any other sort of thoughts?
You can't change the phase until the next cycle.
Ah, okay, so you can't change the phase until the next cycle. Yeah, go ahead.
So if you have a bandwidth of 10 gigahertz, that means you're trying to track within that 1 over 10 gigahertz rate, but your your updates are coming at a much slower.
That's right. So your updates are coming at a much slower rate. What's another way of saying that your updates are coming at a slower rate? And I'll give you maybe a hint. Let's say that my phi ref looked like this, and on this particular cycle, my phi feedback was just about ready to be exactly the same, but oops, turned out didn't actually happen to be wrong until ever so slightly after you sampled it. Okay? What does that mean in terms of when you actually would get that information about when the error happened? How much time would you have to wait? It's not a trick question. Yeah, you have to wait a whole cycle, right? You have to wait another reference cycle until you actually can figure out that, oops, you were late. Okay? Well, if you have to wait one whole cycle before you apply the update, that's kind of like saying that if I take this model here, I could just add this little e to the minus st inside of there, right? And by the way, notice if I've got an entire reference cycle of delay in my feedback path, that very immediately tells you there's only so fast you can make this loop, right? Because if there's delay in your feedback loop, right, if you think about it, let's say, if I tried to make my bandwidth kind of comparable to that reference frequency, that would immediately tell you have 180 degrees phase shift, okay? So it's actually really for this reason that essentially the sampling operation kind of introduces a delay in the loop, that if you really looked at sort of what's the bandwidth you can actually achieve, typically it has to be less than some, oops, actually let me do that. If I have some reference, and let me call it, some reference frequency, divided by some integer factor, okay? Where that integer factor is generally greater than about 5 to 10, okay? So the sort of, let's say, classic thing that people quote is they say, oh, okay, if you're building a Pll or Dll or something like that, the bandwidth has to be less than 10x lower than your reference frequency. That's really where this came from, okay? It really just has to do with the fact that because you're operating with these sort of discrete time quantities, that really introduces delay into kind of the overall analog operation. And that's why the bandwidth is fundamentally limited to those kind of quantities. Okay? Does that sort of make sense to people? Or? Okay, so
What's
yeah.
preventing you from having k equal to 1?
Okay, so let's say k indeed was equal to 1, right? So if I made k equals 1, how much phase shift would I get from this delay here? And remember, this delay is one reference period. What would be the phase shift from that?
1 over your clock frequency.
In phase, I guess. So how many radians, either how many radians or how many degrees of phase shift are you getting?
360.
Oh, okay, actually, so you're right. It turns out that one would be 360. But, by the way, if I've wrapped the complete cycle already, then that means that at a lower frequency, I would already start oscillating, right? Because if you think of sort of the closed loop response, right, I would have already this whole region that has minus 180 to 360 of phase shift, or rather, I should say 180 to 360 of phase shift. That whole region would have positive gain still, and guess what? The thing would oscillate, right? So it really, again, just has to do with this, sort of, let's say, the other intuitive way that you guys are saying it of, I really have stale information. I'm really not working off of anything real. I'm just working off of some totally bogus estimate that came from a long, long time ago relative to the speed at which I'm trying to operate the loop. Okay? Okay, so hopefully this is clear. So, now that we understand that, then we can do sort of a very similar thing with the PLL, and I think many of you guys have seen this before, so I'll probably go through this fairly quickly, but certainly if you have questions, then feel free to ask me. So this is, again, just sort of redrawing what the PLL sort of looks like from a conceptual level. Okay? But really to sort of take this and, let's say, apply kind of the same insights as we did from the DLL, there's kind of only one key thing that we really need to realize. So in the PLL now, what I'm really doing is I'm feeding in some control voltage into my voltage-controlled oscillator, right? So in other words, what I'm really doing is I'm controlling the frequency of the oscillator. But at the end of the day, what I'm trying to measure at the output is actually a phase, right? So now what I really have to do is figure out what's the relationship between sort of my control voltage and the final phase at the output. In other words, the control voltage, and therefore the frequency of the oscillator, and of course, finally, the phase at the output. Okay, so what is the relationship between phase and frequency? And again, you have to think of things as sort of signals. Okay? Anybody happen to know this already? Or?
Integration.
Yeah, it's an integration, right? So just as a reminder why that is, let's imagine that you had some ideal clock at a certain frequency. And let's say that clock looked something like this. Okay? Well, so if my VCO has a certain delta F, in other words, a certain frequency shift from that clock, then even if they initially lined up perfectly in terms of their phases, right, then what would happen is that simply because the period is ever so slightly different, then very quickly what would happen is I'd start accumulating phase error, right? So as an example, that thing right there would just be essentially the delta in periods between the oscillators. This right here would be 2 times that delta, and of course so on and so forth. Okay? So it is indeed an integration between the two. This is actually sort of an interesting thing in that there's many, many places where you'd like to actually put a real integration in your circuit. For example, when I draw these 1 over S's, I assume it's a real integration. Unfortunately, most of them are not real integrators. They actually have some leakage associated with them. But at least if you measure things sort of in terms of phase, indeed, if you actually waited long enough, it would, let's say, the error would go off to infinity. Okay, so this is one of the few things that, in many ways, although not exactly, really looks like an ideal integration. Okay? Okay, so if we keep that in mind, then, hopefully actually drawing the linear model should be quite straightforward. It's sort of, just a direct, let's say, extension of what we did before. So again, of course, we're just going to have some reference clock coming in. We're going to compare that against some feedback clock. So again, this whole thing is really just your phase detector. Okay? Coming out of that phase detector is hopefully, again, some signal either in voltage or current. We're just going to pass that through some sort of loop filter. Okay? And then what we're basically going to do is feed that to the VCO. So in the VCO, And by the way, again, this will still be voltage right here. So in the VCO, there's usually some coefficient that basically sets what's the gain between voltage and frequency. So that's usually called kVCO. Okay, so that's just from volts to frequency, and actually I'll be slightly more precise. I'll actually call this angular frequency. Okay? And then we just feed that into the integration. Okay? So of course the units of this, by the way, are radians per second. Then after we fed that into the integration, this whole thing, of course, is the VCO. That's where we get our final output. And then all we have to do is just feed it back and go through the divider. Okay? So just one other sort of reminder. If I go through a divider, meaning something that just takes in an input clock and gives you a clock that's, let's say, half or tenth or whatever the frequency lower, then actually in phase, you're also dividing by that same factor. Okay, because if you sort of think about it, if I had a fixed number of picoseconds of error at the output, if I compare that to, let's say a 10 picosecond error to a 1 gigahertz clock, if you compare that to a 100 megahertz clock, then that's a 10 times smaller phase error. Okay, so that's why the divider just translates in terms of phase. And that's, of course, what we will finally use to really feed back into this thing. Okay? Does this make sense to people, or? Okay, so now just as, let's say, another reminder. So what will you typically want to put inside of that loop filter? So by the way, if I just made that a unity gain, what would happen in this loop? I just made the loop filter, just not do anything, just have a gain of 1. What would this whole thing kind of look like? Okay, it would look like a low-pass filter, but in particular, let's say that I told you that my reference frequency had some steady state, it wasn't exactly the same as what the VCO frequency was nominally sitting at. So let's say that the reference frequency, and let's ignore the divider, let's assume it's dividing by 1. So let's say I told you that I gave you a reference frequency of whatever, 1 gigahertz, and my VCO nominally was 1.1 gigahertz. So what would happen in this system? What would happen to the output phase? Or maybe to ask it a different way, what's sort of the right way of modeling that in this context? So if I tell you that the input reference has some frequency error compared to the VCO, how do I model that?
Delta F by S.
Yeah, right? I basically said that if I have a frequency error, then that's kind of like saying that my phi ref of S is just delta F over S, right? Because over time it's saying that I'm just integrating that phase error, right? Okay, so now if I feed in that integrated, or basically that frequency error into a first order feedback loop, right? So reminder, first order feedback loop just means I have something like 1 over 1 plus S over omega for my closed loop transfer function, right? If I feed in that ramp into the first order system, what's my output going to do? Is it going to track perfectly with the input ramp or no?
There'll be a steady state frequency error.
Okay, so it turns out there'll actually be a steady state phase error. Okay, because yeah, but you're right that there would actually, so there's a steady state phase error. The frequency would be correct, but the phase would actually lag slightly. Right, so if I just drew a picture of this sort of in time, if this is my phi ref and my phi out versus time, what you'd basically see is that your phi ref was doing this, and I'll draw it maybe in a different color. Your phi out would basically be doing that, okay? And that difference right there would be related to basically the difference between, or really the ratio between that frequency error and the bandwidth of your loop, okay? And for those of you guys, who didn't see exactly where I got this from, just, quick reminder, if you do, your final value theorems and stuff like that, you can immediately get this answer, okay? So given that that's the case, what is it you really want to put into that loop filter?
Another integrate.
Yeah, you want to put another integrator, right? So ideally speaking, and I will actually stick with red for this because we'll fix it in 1 second, you just like to put another integration there. Yeah, okay, so obviously if I just put another integration there, then now I have 2 integrations at DC in this feedback loop. That's bad news. The whole thing will just oscillate. And now, just to trip you a little bit, this is like, an oscillation of an oscillator because the oscillator is not at the right frequency. All kinds of weird stuff would happen, right? So clearly, you have to add some sort of 0 into this. So in reality, of course, this will just end up being something like this. Okay? And to kind of, give the intuition behind this again, what you're really trying to do by adding that integration in is you're trying to drive both the steady state frequency and steady state phase error both to 0. Okay? And then we just have to add that 0 in again just to get the whole loop to be stable, in terms of actually working the way we want to. Okay? Okay, so hopefully that's clear to everybody. I was going to sort of write out the whole Pll transfer function, but I think that's actually sort of boring because I think many of you guys have seen this before. And we may actually come back to it a little bit later on. So if we do that, then hopefully that'll give you the opportunity if you haven't seen it before. But just sort of given what we described already, which was that we said that we wanted the loop filter to essentially have a 0 and an integration. And that essentially the VCO ends up acting like a gain with another integration. Then just to sort of make sure things are clear, if I drew the sort of open loop transfer function, so the loop filter times sort of the VCO's transfer function versus frequency, what would that look like? Just in the open loop. How does it start? How does it end? What does this thing look like?
dB per decade.
Yeah, so it'll start with a 40 dB per decade drop. Right? And then what will happen?
20 dB.
Yeah, and then it'll become a 20 dB per decade wherever you've put that 0. Right? And of course, hopefully if you've done things correctly, you'll do that before the crossover so that you actually have a stable loop. Right? And indeed, that's what it would look like in the open loop. Okay, so now, given that that's the case, if I then went and drew the closed loop transfer function, what would that actually look like? So first of all, what should happen at DC? Somebody other than Shiva. What should happen at DC for the closed loop transfer function? Yeah, it's flat, right? It should just be some gain,
Gain of 1.
right? Okay, and in particular, the gain should actually be the divide ratio. Okay, because if you sort of think about it again, if I have a 100 megahertz reference, and let's say I divided by 10, so I get a gigahertz at the output. If there was a certain phase error at 100 megahertz, it would be 10 times larger at the 1 gigahertz at the output. Okay, or to say it another way, if I had a 10 picosecond error at the input, 10 picoseconds relative to 100 megahertz is 10 times smaller phase error than relative to a gigahertz. Okay, so indeed, gain at DC should be just n. Okay, out at high frequency, what should the thing actually do? What does it look like? Does it go out to n, off to infinity, or what does it do?
Track the open loop, right?
Okay, eventually it will track the open loop. What does that sort of look like? Yeah, it'll just drop at 20 dB per decade, right? So at some point, you just start dropping at 20 dB per decade. Now, there is actually something slightly interesting that happens in the middle. So what is the slightly interesting thing that happens in the middle?
Peaking.
Yeah, it actually peaks a little bit. Okay, so depending upon how you've actually built it, you'll get a little bit of peak here. Okay, that peak is not actually due to instability. It's just due to the fact that if you have a 0 in the open loop transfer function like this, and 2 poles at DC, you have to have this peaking here. Okay, so sort of by definition, the peak gain will always be larger than just whatever you expected from that multiplication. Okay, you can keep that pretty small, but indeed, that's sort of a fundamental thing. It's, you can't really get rid of it. Okay. The other thing I should mention is that now, sort of unlike the DLL, or maybe slightly different than the DLL, indeed with this PLL, I can actually sort of filter out jitter coming from the input. Okay? Of course, if I do that, I'm going to have more jitter coming from the output due, for example, to the VCO. But we'll talk more about that later on. Okay, so sometimes people will sort of use a filter, use a PLL as a quote-unquote filter in the timing domain. So sometimes they'll call it even like a cleanup PLL, meaning they're just using it to try and get a cleaner clock than you had before. Okay?
I thought you can change the KVCO and the W2 to make it overdamped, right? To make the peaking.
So even if
disappear.
you make it overdamped,
Yeah.
all that will happen is the response will look something, and I'll do it in a different color. It'll look something sort of like that.
Oh.
Okay? Because again, that 0, you can't move it around really, right?
So you're assuming W2 is fixed in the. Are you assuming?
Even if I
Okay.
change the overall bandwidth, I still can't get rid of the fact that there has to be a 0 in my passband. Right?
Okay.
That's really the issue.
Okay.
Okay?
Can you put one more pole after that?
Okay, so you could indeed put one more pole, but even if you put one more pole, that pole had better be out over here somewhere. Because if it's not, then, if I put it, let's say, over here somewhere, then guess what? I need a 0 to compensate for it, or again, I'm in trouble. Right? In other words, if I had, let's say, 60 dB per decade here, then at some point I'm going to have to become 20 dB per decade just so that I don't become unstable. Okay? Okay, so hopefully that's all fairly clear, and again, I think this will be, you'll probably get into a lot more detail as you actually start building the things. But I wanted to sort of go into a couple more, let's say, of the issues in terms of when you really look at these components, how do they really work? Because I think they'll elucidate some more of the, let's say, interesting behaviors with these kinds of systems. So in particular, the first thing I want to sort of talk about is just how do you actually do that phase detection? Okay? Turns out there's a lot of different ways you can do it, but almost all of them generally boil down to the same idea. Okay? And the most basic idea is essentially to just create a voltage pulse whose width is somehow related to the phase difference between your two inputs. Okay? So it turns out there's actually one really easy way of doing that. So imagine you took your reference clock, you took your feedback clock, and you literally just fed those into an XOR gate. Okay? And you use that as like your error signal at the output. Okay? So if you sort of think about it then, and let's just draw some examples here. Let's say that my reference clock looked, say, something like this. Okay? Let's say my feedback clock looked something, say, like that. Okay? Well, then what you'd basically get in terms of your error signal would be something that essentially anytime they're different would be high, anytime they're the same would be low. Okay? Just something in this particular case that looks like this. Okay? So oftentimes with these phase detectors, it's sort of useful to draw something that sort of tells you what's like the average error signal that you're looking at. Okay? Because in particular, what you'll typically do is you'll take this error signal and somehow integrate it out, right? Because the information is really stored in how wide these pulses are, right? So what you want to do is sort of figure out how wide the pulse is. That's kind of like saying that you take this voltage and just integrate it or convert it to a current and then dump that current onto a capacitor, because that's just another way of sort of figuring out what was the net amount of, let's say, charge that was stored in that pulse. Okay? So if we were to look at, let's say, the average voltage at the output as being our sort of metric for what the real, let's say, error signal is. Okay? So what would this particular phase detector do as you changed the error into it? Okay? So in particular, let's say that I put in a phase error of, just as an example, of pi. Okay? So in other words, I'm completely 180 degrees out of phase. What would the output of the XOR be? 1, right? It would in other words, it was always going to be at the power supply. Right? So that's why I put VDD on there. Right? That phase error would just be at VDD. Or the average output would just be VDD. Okay? So now what happens sort of in between? So as an example, let's say that I gave you pi over 2 of phase error. Meaning now they're 90 degrees out of phase. What would that average be?
0.5.
Yeah, it would be 0.5 VDD, right? Or half of VDD, in other words. Okay, so I'll draw the point here, but in general, what should this curve look like? How do you connect those dots? Yeah, there should be a straight line. Okay, indeed. You should get a straight line that looks like this. Now, just to make sure it's clear, what would happen if I put in 3 pi over 2 of phase error? What would that average output be? Yeah, it'll come down, right? So in other words, this would also actually be VDD over 2. And this would also have, and okay, I'll draw my dot, let's say a little bit more, big, just so it works. It would also sort of come down like that, and I'm just going to extend my axis a little bit so that I actually hit the line. Okay? All right, so ideally speaking, this is indeed what this thing would sort of look like. By the way, if you put this into the closed loop, where do you actually want it, or rather, where will it really end up operating? In other words, what would be the steady state phase error if you use this inside of a, let's say, phase lock loop or even a delay lock loop? Yeah, it'd be pi by 2, right? Now, why is it that it's not 3 pi over 2? Because 3 pi over 2 seems like it's also, sitting at that middle point, right? So why is it not 3 pi over 2?
Sorry, why is it even pi by 2 in the first place?
Okay. So there's another question, which is why is it pi by 2 in the first place? That's actually another good question. So why do you think you're going to put it at pi over 2?
I mean, it depends on the feedback kind of stuff, right? As you increase the value should.
Okay. We'll come back to that in 1 second. So, but there is another question, which is why does it lock to pi over 2? Any thoughts? Why does it lock to pi over 2?
Because the metastable output is always.
So when I look at this error signal, what do I have to do to it? Or really, what am I going to compare it against?
Error of the phase?
Yeah, so when I take this error signal here, right? We said that what we were going to be looking at was some average value of that error signal, or some average voltage of that error signal. What am I going to compare that average voltage against?
VDD over 2.
Yeah, so typically, you would compare it against VDD over 2, right? Now, why would you choose VDD over 2? What's nice about VDD over 2?
Near range.
Yeah, it gives you the most linear range, right? So if I compare that error signal against some, and let me just, jump around over here, against some VREF, right? If I put that VREF at VDD over 2, then I have the most range either above me or below me, right? In other words, I have the most linear range over which I still respond, quote-unquote, the right way. Notice, for example, if I put that reference at ground, loop won't even work because I have no way to go down, right? If I put it at VDD, again, loop won't work because I have no way to go up, right? So typically, you would indeed put your reference at VDD over 2. If you put your reference at VDD over 2, indeed, you'd lock at pi over 2 phase shift. Okay? Is that clear now, Chintan? Or? Okay, so now the question that we then sort of started to talk about was, well, hey, wait a minute. The reference voltage crosses the phase curve twice, right? Crosses it once at pi over 2, and again at 3 pi over 2. So why is it that you don't actually end up here somehow? Yeah.
The 3 pi over 2 point is unstable equilibrium.
Yeah, that's right. So basically, if you sort of think about it, when I'm in this range right here, I'm getting positive gain out of my phase detector, right? So if I close the whole loop in sort of a nominal negative feedback configuration, then, if I went up in this direction, I would get pushed back down. If I went down in that direction, I'd get pushed back up, right? Well, but now over here, completely the reverse is true, right? Because my gain has now become negative. So actually, over here I would get pushed up, and there I would get pushed down. And if you sort of think about how phases wrap and stuff like that, it means you'd actually end up back over here. Okay? There's actually one more. Oh, yeah.
So if you deliberately introduce a -1 in the system, will you lock to 3 pi by 2?
Yes, so you could indeed introduce a -1, like an additional, let's say, inversion in the loop. But I'd sort of claim that, there's practically speaking no real purpose, or really there's no real difference between 3 pi over 2 and pi over 2, right? Because they're both sort of equivalent to each other. the real more important point is that you don't lock to, like, you can't have two possible lock positions. You only have one. Because if you had two possible lock positions, then it would be kind of a pain in the butt because you'd have to, you wouldn't really know exactly where you landed. That's really the more important point. Okay? There's actually one more issue which is a little bit interesting when you start really looking at these kinds of phase detectors. So let's say that I happen to be at some region really around here somewhere. I have a really, really small phase error. Okay? So let's actually draw those waveforms, and let me actually do it, let's say, in a different color, just so it's easier to see. Okay, so let's say my feedback clock was just like this. So just ever so slightly offset from my reference clock. What would the output of the phase detector look like? Or what would the output of the XOR look like? Ideally. Yeah, it'd have to be a tiny little pulse, right? So it'd be some tiny little glitch thing like this, right? Okay, well, turns out no real circuit can generate an infinitely small pulse, or rather really a pulse that's just too narrow. So in fact, if you actually look at what will really happen with any real circuit, basically below some phase error, the gate will just swallow the pulse completely. Okay, you'll just get nothing at the output. So in other words, what you'll typically actually get is a curve that sort of looks like this. Okay, maybe not quite as sharp as I drew it, but something that sort of looks like that. And of course, you get the same behavior on the other side. Okay, so in other words, this region right here, you basically have a dead band. Okay? Where essentially, if your phase error is too small, you just can't even tell the difference between all of those very small phase errors. Okay? So that's not necessarily the end of the world. And actually, by the way, if I was really careful, you'd probably get some similar behavior up over here on the top as well. Because even if it's 180 out of phase, if there's any glitching or anything like that, you wouldn't exactly go up to the top. But basically, indeed, this can be a little bit of an issue, because basically, when you're initially trying to lock, if you sort of happen to just get unlucky, you could sort of get stuck in these weird regions where you don't exactly have the behavior that you want. Okay? In general, you should really eventually lock because the frequency error should sort of push you out of that bad region. But indeed, this is something to keep in mind because, weird stuff can happen if you don't sort of pay attention to this. Okay? Any questions on this? Or? Okay, so now actually there's one more warning that I have to sort of give you, which is that initially the frequencies may be really, really different from each other. Okay? So can anybody think of some really annoying but nasty thing that would happen if you just happen to get unlucky and the frequencies are really different from each other and you use this kind of phase detector? And here's where you have to play sort of Murphy and think about all the things that can be wrong. I think Dan, made the right hand motions, but we'll see if somebody else can figure it out. So what would happen if your frequencies are really different? And again, I just use this XOR phase detector here. I'll give you guys a hint. What is, how do you tell when you're locked? Like, what does the output of that XOR phase detector look like? What's the characteristic of it?
Square wave.
Yeah, it's a square wave. Right? It's a square wave with a 50% duty cycle. Right? Okay, so how many different kinds of square waves with 50% duty cycle can you come up with? An infinite number. Right? So in one particular example, or one, let's say, particularly annoying thing that can happen, is you may indeed have your reference frequency, which is whatever it was supposed to be. And then you just get unlucky. And what you actually get from your feedback is not the real frequency you wanted, but actually, for example, something that's at half of the frequency. Or even actually twice the frequency, or some other weird thing like that. Okay? Because if you just sort of think about it, if I really ended up in that kind of situation, where this was my feedback frequency, well, guess what? My sort of error signal would end up looking essentially something like this. Oops, sorry. No, that was right. Okay. There we go. It would basically look something like this. Right? So in other words, it would again be a 50% duty cycle square wave. It would just be at the wrong frequency. Right? And then in fact, your feedback would also be at the wrong frequency, and your whole loop would be completely at the wrong frequency. Okay? So this is what's known as harmonic locking, and indeed is a real problem. Okay? So it turns out that because of this, you actually can't really exactly use, at least not by itself, the phase detector I just showed you. Okay? So in general, what you actually have to do is not only detect the phase errors, but detect the frequency error also. Okay? Because if you don't also detect the frequency error, there's just an infinite number of possible lock points you can end up in, and there's no way for you to really guarantee that you'd actually get what you'd like. Okay? So the good news is it's actually pretty straightforward to do that as well. So essentially, instead of just building what's called a phase detector, you'll typically build what's called a phase frequency detector. Okay? So the way these things look is, again, actually fairly simple, but we'll just quickly draw one. So to start out with, I'm basically just going to have two flip-flops. These two are essentially identical. I've just drawn them one upside down. Okay? One of them I'm going to clock by, for example, my reference clock. Okay? And the other one I'm going to clock by my feedback clock. Okay? Then what I'm going to do is, and I'm now going to call this sort of like an up and a down signal. Okay, so up means that you should like move the frequency up. Down means you should move the frequency down. Okay? Now actually the only other thing I'm basically going to do, this is really kind of it, except that when both up and down are high, then I'm going to go in and reset both of these flip-flops. Okay? That's reset there, that's reset there. Okay? So let's just sort of do a quick sketch to see how something like this would work. Okay? So let's say this is my phi ref. Let's say this is my phi feedback. And in particular, this time I'm going to, again, try and sort of do the bad thing we did previously in terms of having the feedback be a completely different frequency than it was before. Okay? So let's say, again, this is what my phi ref looks like, something like this. Okay? And let's say that my phi feedback, from whatever reason, again, was locked at half of the frequency. Okay? Or at least it was initially starting out at half of the frequency. Okay? Well, so now let's look at what the sort of up and down signals are doing. And by the way, this whole thing is a state machine, so you always have to sort of assume some initial condition. But let's assume that the initial condition was that both up and down started at ground. Okay? So if they both started at ground like this, then, if my picture was, really clean, then we'd say that both of these arrived at the same time. Okay? So if both of those arrived at the same time, what are both up and down going to do? Yeah, they're both going to just rise, right? They're both going to go up because I basically just clock both of these flip-flops. Okay? So let's just go ahead and draw that. Both up goes up, down goes up, right? Okay, so now it's always going to take some time for you to get through that AND gate there. Right? There's always some delay. So even though both of them have gone high, they'll stay high basically until that AND gate makes it back and tells the flip-flop, oh, no, sorry, you should actually be ground again. Okay? So in other words, both of these would go high, and then both would go low at some point. Right? Or that pulse width would just be set by the delay through that AND gate. Okay? Now, by the way, in terms of, let's say, the operation of the PLL, or let's say moving the PLL away from the point it was before, if both up and down are high and low at the same time, does that do anything to the PLL, or does it basically ignore it?
Ideally.
Okay, great question. We'll come back to that, maybe in the next set of slides. Ideally speaking, if I really had, a perfect thing, then when both up and down go high or both are low, I would completely ignore it, right? Because I'm always looking for sort of the difference between up and down, right? Because if I tell you to move up and move down by the same amount, then ideally nothing should happen, okay? So at least on this first cycle, looks like nothing really happened, right? But when I get to this next cycle, right, phi ref goes high, right? So up should actually go high. Okay, now that thing is just going to stay high until finally, when phi feedback goes high. Right? Only then, with some, again, delay afterwards, would the up go back down. Okay? So notice that by doing this, now my up has stayed high for sort of like almost an entire clock cycle. Right? And the reason that that's happened is, again, now the frequencies are actually different. Okay? So in other words, by using this so-called phase frequency detector, where essentially I don't really reset the correction signal until I see that I actually got another edge on the other one, now I'm really going to be able to force things to actually lock to the right frequency. Because if you actually just sort of draw this picture out again, you'll see that only when I'm really at the right frequency would I actually get things that, on steady state, should give you 0 error. Okay? Does this kind of make sense to people, or? Okay, now, it turns out there's actually one more problem that this, or maybe not a huge problem, but one more, let's say, issue that this particular design helps to alleviate. So, notice that even when I had 0 phase error, I didn't have to create any 0 width pulses to represent that, right? I now have 2 finite width pulses. And as long as I correctly subtract those pulses against each other, then I should have no net effect at the output. Okay? Now, indeed, when you do that subtraction, you have to be pretty good about it, right? So you really have to sort of not create errors when you do the subtraction. We'll talk some more about that in the next set of slides. But trust me, it's a lot easier to do that than it is to sort of, get these 0 width kind of pulse things out of an XOR gate. Okay? Does this sort of make sense to people, or? Okay, so just one sort of, let's say, final warning that I wanted to sort of give you guys about all this, which is that, okay, so indeed, we really will have to use these phase frequency detectors. But now let's sort of take a look at some of the waveforms that we're going to get out of these things if we actually, again, have the PLL just sort of operating in its normal condition. Okay, and let's just sort of take a look at the waveforms that we'll get on the control voltages. Okay, so let's say I have my PFD. It generates the up and the down signals. Okay? And so to create actually my loop filter, in this particular example, I'm just going to do that with some ideal transconductance stage. We'll talk some more about how you actually build that thing a little bit later on. But for now, just assume that I have some ideal OTA. Okay? And then what I'm going to do is just take the output of that OTA and just feed it to this RC filter here. Okay? So the capacitor is basically just giving me the integration. And the resistor is just adding the 0 in. Right? Because at high frequency, capacitor looks like a short. I just get the resistance. At low frequency, I'm just dumping charge onto a capacitor. Okay? So again, let's actually see what would happen under some given set of waveforms. And let's just say that my up and down signals look like follows. Okay, so let's say up looks something like this. And my down, let's say, looks something like this. Okay, so in this particular example, I just happened to choose it so that in one case you're moving up, and in the other case you're moving down. Okay, let's just say randomly due to jitter or something like that. Okay, so let's look at that control voltage there. What's it going to look like? What is sort of the waveform that you'd get in this particular scenario? And let's just say it starts at some arbitrary position. What's it going to look like? What's it going to do when up goes high and down is ground?
Charges up.
Yeah, it's going to jump, right? Because basically what you're going to do is you're going to have some current coming out of that OTA, going through the resistor, and at the same time charging up a capacitor, right? So basically if I looked at V control, and of course V control relative to ground, it would jump up, right? And then as long as current was actually flowing, then you'd start charging up that capacitor, right? So initially it would jump, and then you'd have that sort of straight line kind of behavior on it, right? Okay, so now once down goes up, now what should the control voltage do? So now, by the way, if down is high and up is high at the same time, I should be having no current out of the OTA. So what should the control voltage do?
Jump down.
Yeah, it should jump down. Now, does it jump down to the same place?
No, to the amount the cap's been charged.
Yeah, exactly. So it's going to jump down by however much and stop at the point where the cap was charged by, right? Okay, so now hopefully it should be obvious that basically the same thing would happen on the second part, just in the reverse direction, right? So when down goes up, this thing should jump down, integrate onto the cap, and then just come back and be, wherever it was before, right? Okay, so this waveform looks kind of interesting, right? Now, there's one thing in particular that I should remind you. So usually, when you do a PLL, not always, but typically speaking, you're actually going to be running the VCO itself at a much higher frequency than you are these reference, the reference clock that you have, right? So in other words, if I looked at, for example, the VCO, let's say just nominal waveforms, maybe they would look something sort of like this, right? So there'd be a bunch of VCO cycles during this weird behavior you have on that charge pump voltage. So it turns out this is actually going to cause a little bit of a problem, okay? Because basically what you'd like to have happen, if you sort of think about it, if you want the jitter to be as small as possible, what you'd like to do is make it so that every single one of these cycles on the VCO kind of looks the same as all the other cycles, right? So in other words, if I was going to do something to kind of move the VCO, what I'd really like to do is move all of the edges by sort of the same amount, right? Whereas if you sort of think about this waveform here, remember this control voltage directly translates into what's the frequency of the VCO, okay? So if I actually looked at what would come out of something like this, what I would basically get is kind of during this period here, I'd have a bunch of short cycles, and then during this period here, I'd have a bunch of long cycles, right? And similarly, of course, during this period here, I'd have a bunch of some long cycles, and then again afterwards, I'd have shorter cycles, okay? So what this is kind of really getting at is that basically any time you make a correction, if you were to really just do exactly what I'm drawing here, it would still work. It's not that, it wouldn't work. It's just that, if you really looked at the instantaneous, let's say, and I'll just draw it as a plot. If I plotted, let's say, the instantaneous frequency versus time, right? And this thing obviously will sort of repeat every reference cycle. You'd see something that might look something like this, okay? And then, of course, on the next reference cycle, we'll do something the same, and so on and so forth, okay? So what this is kind of getting at is that even though everything still works, remember we said that we cared a lot about high-frequency jitter and sort of what were the narrowest pulses we got out, right? Well, this kind of behavior is kind of bad, right? Because it means that every reference cycle, every time we sort of make a correction, we're either going to get a pulse that's longer and then subsequently pulses that are shorter, or we're going to get pulses that are shorter and then subsequently pulses that are longer, okay? So turns out this is not exactly the most desirable behavior in the world. You'd really actually like things that essentially you just spread everything out so that all of the VCO clock cycles, no matter where in the reference period they are, look similar. And by the way, for those of you guys who are wireless guys, this is perhaps even worse in that context because this is what's called a reference spur. Okay, so it means that every reference clock cycle, something different will happen than the other cycles, and that just creates sort of a tone in your clock spectrum, which can then mix with all kinds of other stuff and just bad news. Okay, so you really don't want to have this happen, but good news is there's a fairly simple fix. So what's the typical fix that you might apply, or what conceptually, what do you think you want to do to try and make it so that things are much more uniform over that reference period?
Low-pass filter.
Yeah, what you basically want to do is low-pass filter the thing, right? You want to kind of smooth these spiky waveforms out. Okay, so how do you do that?
Put up cap over there.
Yeah, you put another cap. Okay. So indeed, and this is just because now I'm lazy. I didn't want to redraw the whole thing. Basically, and sorry, you guys don't get it, but feel free. You can draw if you'd like. Okay. What you basically really do is indeed just add an extra capacitor. Okay. So this is usually what's called C2. Basically, what you're really doing is building a higher order loop filter. Okay. So in this particular case, this would be like a third order loop filter. Okay. So the idea is that by doing this, now instead of having sort of the red waveform that I've drawn here, hopefully you could instead take it and make it look something more like that. Okay? And of course, similarly on the other side, something that would look more like, let's say, this. Okay? Now remember, ideally speaking, what we really wanted to do was kind of spread this over the entire reference period. But indeed, there's actually sort of only so much you can really do that. Okay? At least with this particular implementation. So the reason for that is that, remember, this is indeed going to be adding another pole into your forward transfer function. Right? So if I still want my loop to be stable, there's only so low of a frequency I can put that pole and still make sure that everything will actually work correctly. Right? So in particular, if you sort of look at, let's say, practical values, typically speaking, that C2 relative to your main sort of integration capacitor has to be less than about 1/10. Okay? So in other words, your main integration capacitor typically has to be about 10x of the sort of second or third order capacitor that you added. Okay? Because again, if you made that capacitor sort of too large, then now that would become sort of the dominant pole, or in fact would even sort of, or I shouldn't say dominant pole, but basically the phase shift because of that extra capacitance will start coming into your loop and destabilize the whole loop. Okay? Does this kind of make sense to people, or? Okay, so for those who are interested, turns out there's actually lots of additional tricks you can play. So there's actually even tricks where you can really spread the correction over the entire reference cycle, but they usually involve introducing an extra sampling operation. Okay? So what you do, for example, is just do this integration first, and then dump it onto a capacitor that would be having the same value over the entire cycle. Okay, so these are usually called sort of sampled loop filters or sample reset loop filters. There's a few different ways you can do it. Usually, once you've sort of added this capacitor in, at least in the high-speed link context, this sort of does the job well enough that you don't have to do too much more. But again, if you really care about those spurs, then you might actually have to do some more sophisticated techniques to really get it completely knocked down. Any questions on this before we sort of move on, or? Yeah.
I'm still a little bit confused. The jump is due to the charge sharing?
No. So the jump is, right, if I looked at this thing, right, if I just have a resistor and a capacitor. So if I just take a current and I dump it into a resistor capacitor like this, right? Okay. The voltage on that cap can't change instantaneously, right? So I just have a current flowing through that resistance. So that jump is exactly just I times R, right? Is there a question in the back, or no? Okay. Any other questions on this, or? Okay, so let's just briefly start looking at some of the next set of slides. Okay, so we've kind of started talking about these things already, but what I wanted to do now is, hopefully now that we have sort of a general idea of kind of what these PLLs look like, now I wanted to really sort of start diving into more detail on what are the different components and what are some of the issues in terms of how you'd really build those up. Okay, so the first thing, which I kind of hinted at a little bit, is that you don't really usually build the PLL the way that I sort of drew it the slide 1 second ago. Because building that transconductance stage deals with rail-to-rail inputs and really subtracts them properly, if you really did that kind of the traditional way, it doesn't exactly work usually the way you want it to. Okay? So instead, the way that people usually actually build these is what's called a charge pump PLL. Okay? So, and I'll just sort of draw a quick block diagram of the thing because I think that will sort of make it all clear. So again, let's say I have some reference, I have some feedback, I feed it into my phase frequency detector. That phase frequency detector generates up and down signals. Well, if you sort of think about it, all that transconductance stage is trying to do is basically push some current into that loop filter if you're trying to move up, and pull some current out of it if you're trying to move down, right? So in other words, you can kind of conceptually think of this as just, if that up just controlled some switch, connected to a current source, and that down also connected some switch connected to a current source. And then I just took that middle node and I fed it into my loop filter, which again, I'll probably do some sort of third order loop filter there. And then, of course, feed that into the VCO, have that, come through a divider, and feed back. Okay? So it turns out that at least over, let's say, the last maybe 20, maybe even actually 30 years ago or so, this is really the sort of most standard PLL architecture out there that you'll see. Because it turns out this charge pump is just kind of a convenient way of implementing that quote-unquote transconductance. Because again, at the end of the day, all you're really trying to do is just either push current in one direction or pull it out in the other direction. Okay? And then essentially all you're really doing is you then just take those currents and filter them through this loop filter. Okay? Does this sort of make sense to people? Or? Okay, so let's just see how you'd actually build this charge pump. And I'll be nice to you guys. I'll give you a reference current to begin with. And I'll assume that it's even actually the right reference current for whatever it is you're trying to do. So how would you build this charge pump? What's like the most straightforward way for you to do it? Okay, so I have two switches and two currents. How do I actually build them? Give me some transistors. I mean, you're right. It's two switches and two current sources, but how do I actually build that? Okay, well, so let's just draw something. So you said I have a current mirror. Okay, so that's a current mirror. What else do I do? By the way, if you want, switches somewhere else, just tell me, and we can add those switches in. Ah, okay, so you could do it that way. Let's actually, what's the even, let's say, more lazy way of doing it? So let's say I don't want another switch there, but you could indeed do what you're saying, but, let's say, what's another way of doing it? Okay, so it's kind of like a tri-state, but by the way, I'm only pulling current down, so what do I do? Yeah, I just put a transistor in series with a current source, right? By the way, there's many other ways you can do this too, but this is actually just one particular example, and we'll see sort of some more of the fun that we're going to get into. Okay? So by the way, what's that transistor controlled by? When do you want that switch to be on? Yeah, when down is high, right? Okay, now what do I do? Yeah, okay, so I'm going to take one more copy. And let's say I do it like that. And okay, so I'm going to be feeding it to some Pmos. So I guess I'm going to have some mirror over here like this. Okay, and so maybe I do this, and now, anything else I need on that Pmos? Yeah, another switch, right? So by the way, what kind of switch is that going to be? Yeah, it's a Pmos switch. Okay, so what's that going to be controlled by? Yeah, it's up bar. Okay, so that's already, let's say, one practical annoyance. And by the way, just so it's clear, the loop filter is going to sit out over here somewhere. So now this is already one, let's say, practical annoyance, which is notice that to actually get this to work, I couldn't just directly take up and down, but I actually have to deal with up bar and down. Okay? So in general, what you actually have to do is some sort of phase splitter or some sort of delay matching kind of thing to make sure that really this up bar behaves the same way as down does, even though the logical polarity had to go through a flip. Okay? That's life. It's not too bad as long as you're careful about it, but just keep that in mind. Okay? Because if you don't fix that, you can get all kinds of fun errors. Now, it turns out, even what I drew here is not quite such a good analog design. So anybody detect any other, let's say, not so good things that I did when I drew this? You guys both kind of said it. So you said the mirror is not good, and you said there's no cascode. So why, when you say cascode, what do you mean?
Yes. So the mirroring devices, if you want to improve the gain error or the mirroring, minimize the mirroring error, you should cascode due to the RO of the devices. Okay, so you said you should cascode them. It's kind of related to that, but let's see if maybe Shiva, any other thoughts?
Cascode.
Okay, so you're right, you could indeed just cascode, but there's one, let's say, conceptual error that I, let's say, banged on quite a bit on 240. So when you want things to match, yeah.
So the impedance on both sides of the switches need to match for charge injection?
Okay, so you actually even took it, 2 steps beyond where I was going. So you said the impedances actually need to match for charge injection. That's absolutely correct. But there's even one more, let's say, conceptual error here.
You only need 2 transistors on the left-hand side, but you have 4.
Yeah, exactly, right? Remember, I said I want things to match, and anytime they have to match, they have to be exactly the same. And exactly means exactly, okay? So the conceptual error in this particular drawing is that the actual switches I'm using, or the actual current sources I'm using, have stuff in series with them, right? They both have something in series with them. Okay, so if you really want to do this conceptually correct, you actually need to put those switches in there too. Okay? By the way, if you're really going to do this right, you better put the switch even in this mirror branch also. Okay, because whatever's generating that reference current isn't really exactly perfect either.
That should be on top, right?
Which one? The
diode
diode? Well,
yeah.
in this particular case, I'm really operating this as a switch. If I was doing it as a cascode, then you're right. But if it's really a switch, I could do it like this. You're right,
It's not really
technically.
buying you anything, right?
Technically, I could do this, but it's not. In this particular case, it's not, let's say, super critical. As long as I'm consistent, then I'm sort of okay. But you're right. There's nothing wrong with doing it this way.
No,
either.
but if you do it the other way, the VDS is. I mean, it's the cascode is not really doing anything then.
Oh, but who said this is a cascode?
Sort of.
Yeah, no. So you're right. You could indeed tie it that way. Again, don't get me wrong. You could indeed tie it this way. But don't forget this whole thing is actually sort of, you're turning these switches kind of on and off dynamically. You get charge injection when you do it. So there's actually, let's say, lots of other fun issues. But the first thing that I really wanted to sort of make sure is clear is anytime you want things to match, you better make sure they're really exactly the same. Okay, so even if, let's say, you do something like this, and let's say you do something like that, better make sure you actually have the same in all of those branches of current. Because if nothing else, even just the variations in poly resistance will cause you, or excuse me, the poly etching will cause things to not exactly match if you don't do it the right way. Okay? So we'll actually sort of talk a whole lot more about this next time. So unless there's any other questions, I'll see you guys on Thursday.